the switching between transparent and reflective states in dielectric cylindrical metal lattices, and it will be given by Dr. Suhandoko Isro from ITB. Let's welcome our speaker.
Yes, thank you, Professor Shin. Now I will share my screen. Okay, ladies and gentlemen, good afternoon. It is an honor for me to be here with you today and to share one of my latest research with you. So my work is about switching using a metal lattice system. Ladies and gentlemen, display technology has been everywhere in our daily life. And one example of display technology is the Videotron or the Megatron like this, that is usually used for doing advertisement. Unfortunately, this kind of Videotron consumes a lot of energy. During the day, when sunlight is very bright, we have to make the Videotron to be as bright as well. Otherwise, we cannot see the content inside the Videotron. Now, the idea here is instead of opposing the sunlight, why don't we use the sunlight or the ambient light to be the light source for our display or our Videotron? And one way to do that is by using a metal lattice system. So what is metal lattice? When we use the word lattice, most certainly we will be talking about the periodic structure. And likewise, here our system is consisted of parallel array of tubes, which are arranged periodically to make the metal lattice system. So each tube here is parallel with the z-axis, and they are periodic in the x direction. One unit cell consists of one single tube, and each tube is made of a dielectric core, which looks white here. And the dielectric core is covered with another material, which looks red here. And then we illuminate this system with plane wave, and plane wave is incoming in the negative y direction. And the plane wave is polarized in a way such that the electric field is always on the xy plane, and the magnetic field is always parallel with the z-axis. And we call such polarization as transverse electric polarization. What we will try to do next is we will vary the refractive index of the core material in the hope that the system will show some response upon changing the refractive index of the core material. And hopefully that response will be useful for us. Later on, to observe the response of the system, we will look into the transmittance or reflectance spectra of the system. So now how do we conduct this study? We can actually conduct this study in a theoretical basis. We simply use the Mie-scattering theory, or some people may call it the multiple scattering theory, but we do it in cylindrical coordinate system. The difference here in our calculation is that we introduce Bloch theorem into our calculation. Normally, when the number of structure is limited, each structure will have different scattering coefficient. But now here, since our system is periodic like this, we can immediately see that the scattering coefficient of tube number L is simply just the scattering coefficient of the central nanotube multiplied with an exponential factor, which has the information of periodicity of the system. Periodicity here is D. And then once we have our complete solution of our wave in cylindrical coordinate, we can convert back the solution in cylindrical coordinate into the solution in Cartesian coordinate. And then by doing so, we can later on calculate the transmittance and reflectance of the system in a standard procedure in standard way. For more detail about calculation method, we can refer to this reference. Now we have to consider the geometrical and optical parameter of our system. Let's say, suppose for now that each tube has outer radius of R. R later on can be any number, and we can leave it for now. And for the inner radius of each tube, the radius of the core, we take it to be about half of the outer radius. So why do we take this number? So why do we take this value? Remember that later on, we will try to vary the refractive index of the core material. So if the refractive index of the core material, so if the size of the core material is too small, probably the effect of changing the refractive index of the core material will be negligible. But then on the other hand, if the size of the core material is too big, probably the effect of the layer material will be insignificant. So about half of the outer radius is just a good option. As for the interparticle distance, we cannot make it too big and we cannot make it too small. If we make it too big, then there will be no coupling between particles. If there is no coupling between particles, then the result that we will get is simply just the result of misscattering for single particle. On the other hand, if the interparticle distance is too small, it will be impractical. It will be not realistic experimentally because we know that each structure here will have surface tension, and that surface tension can cause aggregation if interparticle distance is too close to each other. So we take it 2.8 of R is just about a good option here. And as for the wavelength, we take the range of wavelength to be around this range from 3 times R to 11 times R. And again, why do we take this range? It's because we want to make sure that the wavelength is larger than the size of the tube and larger than the interparticle distance. We do that because we want to neglect the effect of classical diffraction. We know that if the wavelength is smaller than the size of the tube and smaller than the interparticle distance, then our system will look like a standard grating, and there will be the effect of classical diffraction. So here, to neglect the effect of classical diffraction, we make the wavelength to be larger than the size of the tube and the interparticle distance. As for the optical parameter in our system, we assume that the layer material has refractive index of 3.4, and for the core material, we will try to vary the refractive index starting from unity. Now here we are looking at the transmittance spectra of our system. The solid line is the transmittance spectra when the refractive index of the core material still equals unity, while the dashed line is the refractive index of the core material. The dashed line is the transmittance spectra when the refractive index of the core material equals 1.7. Now we have to pay attention to the range of wavelength, where the wavelength is about 4 times R here. Here, initially, when the refractive index of the core material still equals unity, the transmittance of the system is very high, even equals to unity. And this means that the system is transparent. But then when we change the refractive index of the core material to 1.7, here the transmittance becomes very low, it goes to 0, which means that the system is no longer transparent, or in other words, it has become reflective now. So here we find the phenomenon of switching from transparent state to reflective state, and we can do that just by varying the refractive index of the core material. Suppose now we say that transparent state occur when the transmittance of the system is higher than 90%. We can immediately see that it means that this switching phenomenon occur not only at a single wavelength, but it occurs at a band of wavelength. And that reflects the robustness of this phenomenon. So what does this result has to do with the Variotron thing that we talked about earlier? Well, because we are using dielectric, the effect of size is simply just to shift the transmittance spectra. So for example, if we use tubes with small diameter here, the transmittance spectra and the working region of the switching phenomenon will lie on the shorter wavelength. But then if we enlarge the tubes, the transmittance spectra and the working region of the switching phenomenon will occur on the longer wavelength. So the transmittance spectra are shifted to the longer wavelength. They are redshifted. The ultimate idea here, of course, is to build an RGB system, an RGB pixel, which are made of the metal lattice, which are made of the nanotubes. For example, here, the blue pixel is made of nanotubes with smaller diameter, and the green and the red pixel are made of tubes with larger diameter. The idea here is when sunlight or ambient light hit the pixel, if you want to make it appear blue, simply just switch the blue pixel to its reflective state, and the blue light will be reflected, while the green and red light will not be reflected. If we keep the green and the red pixel stay in the transparent state. That's the whole idea, but to implement this idea, we still need further research. we can make some conclusion from the research. First of all, the dielectric metal lattice system can support switching from transparent state to reflective states. Secondly, the switching can be obtained by varying an optical parameter, the refractive index in the system. Third, the switching phenomenon occurs in a band of wavelength, not only at a singular wavelength. And then last, we can use the switching phenomenon to build an RGB pixel, which uses the sunlight or ambient light to be the light source. And to end my presentation, I would like to thank, I would like to thank the Ministry of Research and Technology of Republic Indonesia for funding this research. I think that's all my presentation. Thank you very much for your attention. Good afternoon.
Thank you very much for presenting us a very interesting proposal of novel reflective displays. It seems to have huge contrast ratio. Now the floor is open for questions. Yeah, we have one question in the chat window.
Okay, thank you, Professor Martin. Yeah, we can do a non-normal incidence as well. We can do oblique incidence, but for now, we want to concentrate on a perpendicular incident wave for the first time.
So maybe for the non-normal instance, the period might have to be reduced a little bit because there could be some diffraction appearing.
Yes, I think, of course, the periodicity of the lattice system has to be smaller than the wavelength so that the diffraction effect can be neglected. Is that what you are asking, Professor Shin?
Yeah, for normal instance, that's the criterion. But for off-normal instance, because the instant wave can have non-zero in-plane wave number, the diffractions can still occur even when the period is less than one wavelength.
Okay, thank you.
Yeah.
Thank you. All right.
Is there any other question from the audience? So I have one question. What would be the candidate material for the core? The most promising material or solution?
Okay, as for the core, because we have seen that the refractive index of the core material is very low, we actually envision to use liquid materials inside it. Yeah. That's why we make the structure to be nanotube.
Yeah. Great. Is there any other question? Okay. If not, let's thank Dr. Isro and all other speakers in the session.